In terms of the talk, what I wanted to do is start off with kind of laying out where does postmortem debugging fit into the different set of methodologies that people use with debugging today. I wanted to go over some basic tools that people use for postmortem debugging across languages and what they look like. And then finally, I wanted to talk about why just a lot of people don't use it and one of the problems around it. And then finally, I wanted to end the talk with actually a case study and a paper that was done by Microsoft about a postmortem debugging system they built and some of the interesting things they found out about. So debugging methodologies. Let's start off with the first and the easy one. That's interactive debugger. In some cases, people call it an in situ debugger, but it's basically the typical REPL that you guys are used to. So, next, print, etc. Instrumentation and tracing. So this is stuff like perf, strace, and we'll talk about why you'd want to use instrumentation in a second. There's the typical logging, the classic printf statement that people use. And then finally, the star of the show today, which is postmortem debugging. So interactive debugging is great for development and reproducible bugs, but it's terrible everywhere else. So you don't want to use an interactive debugger in production. You don't want to attach a debugger to a live database. It's going to slow everything down. It's going to ruin your night and day. The next methodology is instrumentation. Instrumentation is really powerful when you have a live running system. Let's say it's not logging what you want to log, but you want to extract or coerce data out of that running system. It allows you to observe internal state, things like execution path and events over time. So I was talking before about perf, the perf profiler. So you run perf on a process. It will actually give you frequency distribution of the functions that it observed over that time. You can also use perf to observe PMCs, other sort of system events. And this is really powerful when you're trying to guess what's going on. I'm sure most of you have dealt with perf, and it's a really powerful thing. The problems with instrumentation and tracing is that there's a lot of overhead on the live system. You're actually doing this on the system the workload is happening, which the overhead includes both extraction and capture, as well as the post-processing of it. It's possible for you to take these asset files and actually post-process them on different systems, but typically what you want to do is either use the debug symbols available or use any other assets on the system for you to be able to report on the data that you captured. And the idea of instrumentation really is centered around one-off investigation. So you typically use it when bad stuff happens. So when you're not seeing the kind of behavior you want to, you launch up your profiler and you try to go at it. Logging is one of our favorite ways of debugging. It's easy to use. There's a lot of existing systems to be able to ingest, aggregate, and analyze. So I'm sure all of you have heard of Elk, Splunk, Logstash. And it allows you to be explicit about errors. One of the nice side effects of logging is that it kind of documents your code a little bit. At least that's what a lot of developers tell me when they don't document their code. Cons is that it's really rigid and inflexible, meaning that you only get the information that you explicitly elect to log. That could be through your own internal accounting. This could be very powerful. However, it's still only what you want to log. And it's not easy to log, and it's not easy to serialize and represent highly dimensional complex data. So things like not only just a stack trace, but also things like a linked list or variables or, let's say, slice. It's not easy to log all of them out and have them in an easy to represent standard way that's structured, that's universal across your program. I've unfortunately, you can't actually see the red that well, but this is code that I've written multiple times, several times. It's basically saying, in a comment, this should never happen, and then printing out in a log statement that something bad happened when it does. This is the way I view logging in a lot of cases. I kind of anticipate what's going to happen, and then I log that if it does happen, let me go ahead and log it. These different methodologies all solve a particular issue, particular type of bug or particular cases. What I wanted to talk about was now postmortem debugging, which actually tries to solve another set of use cases, but also you can mix and match. Before I do that, I wanted to give a little history on postmortem debugging. It dates back to the dawn of computing in 1951. This is the picture of the Whirlwind 1 computer out of MIT. And the idea of postmortem debugging is, at the time of error, a complete state of the application is captured and saved for later investigation. I should underline or italicize complete, because there are postmortem debugging systems that don't necessarily give you the complete state of the application. However, what they do is they give you a much more rich and much verbose set of information beyond logging or instrumentation. The cool thing about the Whirlwind 1 computer is also where we get this idea of the core dump, and that's because it was the magnetic core. Literally what they would do is they would actually output the information stored there in octet form to a CRT monitor. And then they would have a camera take a picture of that monitor at that time. And then they would have developers debug via a picture, essentially. So the idea of a core dump representing a snapshot of your application kind of comes from this process. Postmortem debugging, and what are its pros and cons? Gives you a very rich data set. So when I say the complete state of the application, I do quite literally mean in most cases it's a complete replica of the memory space of that process. It's a robust data capture method. So this does not rely on an internal library. It doesn't rely on your logs getting somewhere. You're actually relying on facilities provided either by the language runtime or provided by the operating system itself. There is overhead only at the time of error, so only when you want to actually capture the complete state of the application, which is different than, let's say, your instrumentation or your logging. And what this allows you to do, in most cases, it's at some point contained enough so that you can do this analysis asynchronously, which allows you to do very powerful tooling as well, which we'll go into later in the presentation. The cons is that if you've got the full state of the application serialized, it's obviously going to be a huge dump of information. And for languages like Python and Java, which we'll go over, there's actually a lack of tooling and documentation onto how to utilize this dump of information. So I stole this slide from one of Brian Cantrill's talks about debugging. And I think he did a really good job about kind of setting the space about types of errors. So we have our x-axis, which is non-fatal and fatal, and then we have implicit and explicit errors. So the terminology is pretty self-explanatory, but if you have a fatal error, it's something that's going to cause your application to stop executing. Non-fatal is something that doesn't make that happen, and explicit is something that you know beforehand that you can actually be indicative of, whereas implicit is not the case. Typically, the way that I've seen it talked about is on the right side, everything that's a fatal error is going to be something that you want to use postmortem debugging for, and where postmortem debugging can be very powerful. Logging is typically for your non-fatal explicit errors, and then instrumentation is for the top left-hand corner, implicit and non-fatal errors. That said, it's not as clear-cut as that. You'll see cases where people will actually use postmortem debugging for explicit non-fatal errors. You'll also see cases where people use postmortem debugging for implicit non-fatal, or logging for fatal explicit, and they're just hoping that the logs get through. I wanted to give this little gem here, because I was doing a lot of research on Golang before I made this presentation, and I found this on Stack Overflow. The best part of this is that he said he put this at the beginning of every function, and then in order to prevent my program from crashing. Now I'm wondering, is this really the way to go? And the best part is that you look at the code and all he's doing is printing the error to prevent, he captures the error and then prints it, and that's all he does when he anticipates a crash. So that's always, sounds like a fun debugging experiment. Also, another thing that I love to do is pick on people, and so people who write in Go typically say that their stuff doesn't crash. So I took 3 pretty popular open source projects in Golang, and I'm not going to call them out. And I researched the word panic. Panic is a fatal error in Go. And so I saw things like 43 opened, and the oldest one being May 5th. So this is indicative not only of the fact that even in your higher level languages, you do see these fatal errors, but they're also pretty gnarly errors as well. So when you see these kind of Go panics, or you see these uncaught exceptions, they can be very difficult to debug. And that's because you can't necessarily rely on the tooling available within the language or the system to be able to operate within some of these scenarios. Going back to this talk again, like I said before, bottom left hand, so bottom left quadrant is where logging really shines, but I've seen logging used for things like fatal explicit errors as well. Tracing, obviously, is used in a lot of different cases as well. So is there a clear choice on when to use postmortem debugging versus logging versus instrumentation? And the fact of the matter is there's not. People use logging for fatal errors. People tend to use what's familiar to them. And so if they have a tool that they really love and it's available to them, then they're going to use it. And that's part of the problem with postmortem debugging, and that's why we don't see a lot of it today. When I talk about the problem with postmortem debugging is the familiarity and availability of tools. So with C and C++, you kind of have full support for this stuff. Native support in your common tools like GDB and LLDB, and there's a lot of core dump analysis tools in the form of either debugger extensions, so Python scripts for GDB, or standalone products. But for something like Java, typically you have JStack and JDB, which do have support for Java core dumps. However, they are very difficult to use in my experience. You do have a really cool tool with Java heap dumps with Eclipse Mat. And it's cool because you can do a couple of things with the memory analysis tool from Eclipse. It provides a query language for you to actually query the state of the heap dump. So you can say things like, show me all of the objects that reference this specific object, which is crucial with the GC type language because you might have live references and you don't know where those references are coming from. You can also generate a dominator tree, as they say in Eclipse Mat, which actually gives you this hierarchy of references to be able to investigate GC issues. I put the flags that you'd want to pass to the JVM to be able to get a heap dump from Java that you can pump into Eclipse's Mat. Python, unfortunately, the story is not as good. So there's a set of GDB scripts that allow you to inspect Python core dumps. If you're not familiar with gcore, what you can do is on your Python process actually call gcore. And there are I believe there's some Python utilities as well to actually invoke and cause a core dump. And then you can load that core dump into GDB with these Python scripts. There's also PyHeapDump by Anselm. He actually gives a really good presentation on this. So I'd recommend you look up Anselm Kroos and PyHeapDump to investigate some of this stuff. This is also really powerful because, like Java, it allows you to inspect what's on the heap and be able to investigate leaked resources. For Node.js, which I actually didn't see anyone say that they do any JavaScript in Node.js, but so the guys at Adjoint have done a lot of really good work with an MDB debugging module. So MDB is available on SmartOS and Illumos. I'm not sure if it works on Linux yet, but they provide a lot of extensions to MDB to be able to inspect JavaScript, postmortem, or core. Powerful stack and heap inspection. So when I talk about that, there's actually a really good presentation by the guys at Netflix on how they use these tools to find memory leaks in through their core dumps. And that's one of the reasons why postmortem debugging can be really powerful, which we'll talk about in a second, is having a complete state of the application actually gives you a point in reference. And so a point in time, what was my application doing, and actually having a full state of the heap allows you to use that kind of like as A/B analysis. So if I have another core dump, can I compare the two? And I can actually see the differences within the number of objects that I have in the allocations. With Go, there has been some support from the Joyent team that was added to MDB. We at Backtrace actually have something available, but unfortunately, according to the docs, GDB does not understand Go programs well, and this is from the Golang docs itself. And basically, they're saying that we're not really focused on this right now, and we'll think about this later when it becomes a bigger problem. So we have this awesome debugging methodology. So we have this thing that says, I don't need to explicitly log what the information I need. I don't need to add overhead when I'm trying to do tracing. I can get the complete state of the application for a fatal error. But how come we don't use this more in practice? How come we don't actually try to get core dumps from live processes and try to expect them? So this is the part of the talk where I was going to give an awesome war story about some C web server that I wrote that had a pretty gnarly bug and having to debug it. But I figured that that doesn't really get to the point as to why people don't use postmortem debugging anymore. It surely says that I'm not the best at programming, and I have bugs in my code. But the reason why people don't use postmortem debugging is because it's very difficult to actually do detection and retrieval of this data. So when you're running a Python process and you actually want to generate a core dump, a lot of cases you have to do it manually through gcore. You have to add additional flags to your JVM to be able to get the heap dump as well. And so people don't add this because it's not their first tool of choice. The next part of this is that you need the tooling and the knowledge to be able to interpret this information. If this is something that you don't do over and over again, then it's going to be very difficult for you to add this into your repertoire of tool sets. And the last thing is that with postmortem analysis, it's typically when my program has crashed. And so it's when I only want to find the root cause of the crash and nothing else. But there's all of this wealth of information that people just don't use in their postmortem assets. And so for these reasons, many people choose to use more readily available methodologies. The way I see it, though, is that, and the way that I have this kind of love-hate relationship with postmortem debugging is that these are all solvable operational problems. What that means is that this isn't necessarily a problem with the act of postmortem debugging and the power that it has, but these are things that we can actually solve by changing the way we go about collecting and actually operating on this data. But why does that matter? I mean, we live in this world today, and no one's really doing this. Do we have an example to look for to actually see the kind of power that can be done with postmortem debugging at scale and to go through these operational problems? Fortunately, in a very ironic way, we have something to look for, and that's Microsoft. And if anyone did not get that joke, it was very subtle. It's a Star Wars reference to A New Hope, but people kind of think of Microsoft as the dark side. So it was a little ironic. I'm glad I had to explain that joke, too. So Microsoft published this excellent paper in 2009 called Debugging in the Very Large. And the way they describe the system that they talk about in debugging in the very large is they say it's a postmortem debugging system. This was the postmortem debugging system they built for Microsoft Windows and Microsoft Office. So you can think of this as a massively deployed system that, obviously there's not a lot of coordination between nodes, but they have quite a bit of volume, quite a bit of complexity, both in Windows and Office. And the way this system came about is Microsoft Windows had this web page where you would actually, every time you get the blue screen of death, there would be an asset that would be dumped on disk, and you'd go to this website, and you'd actually upload this kind of core dump or this kernel information. And so they would then allow you to upload it, and they would have this backend system that would do automated analysis on top of this dump. And they thought that was great. And then Microsoft Office had this other thing where they didn't actually require you to upload the dump. What would happen is that a small, I think it was the clipboard thing or whatever, would say, do you want to submit this error report? You'd say yes, and they would submit it to a system. But then they did no automated analysis in the back end. And so Microsoft said, hey, why don't we combine these two systems? And that's what came about with the Windows Error Reporting solution, so WER. So with Microsoft, they had thousands of developers, and they're trying to scale out their development team and specifically scale out debugging. This is complex software with a large volume of installations, millions of computers running Windows and Office. It was guided by 3 goals. The first goal was automated error diagnosis, which is really awesome if you think about it. Think about your software crashing and then being able to actually automatically diagnose what the error is. It wasn't perfect, and they said a large part of the system was actually intuition-based, but it really dug deep and actually exposed a real-world use case of algorithmic debugging used by a pretty massive company. The third goal was progressive data collection. So for them, they didn't want to collect a full dump, a full core dump from every time you got the blue screen of death or every time your Microsoft Office crashed. What they wanted to do was they wanted to say, if I've seen this error before, don't give me the full dump. Generate some sort of signature so that I can identify its uniqueness. And then if I want more information, have this kind of feedback protocol where I can gather this information. The last third goal, which I think is one of the coolest ones, is statistics-based debugging. And so it's kind of flipping or shifting the way we think about debugging away from intuition-based and more to a statistics problem, and thinking about ways of correlating variables and actually using the depth of the information from this dump to be able to isolate variability. The really interesting part also was that Windows error reporting was not used just for crashes. It was used for hangs, it was used for install failures, and they provided an API for developers to actually generate a dump from a running application. So essentially, imagine an API call saying trace me. So it would allow for runtime non-fatal errors as well, and the capture of information of that. Before I dig deep into the operation of the system beyond these three goals, I just wanted to show a quick diagram from the paper. And so this laptop at the top, assuming you're running Microsoft or Office or Windows, it would generate this, what they call a label or a bucket. And then it would send this off to their front-end IIS servers, which are just web servers, to say, have I seen this error before? What do I want to do with this type of error? It would then hit their online job servers, which would go about and actually what they call do more labeling heuristics. The point of labeling heuristics or generating this signature was so that they can actually determine uniqueness on a greater level. So just because you have the same stack trace from an error does not mean it's the same error. It could be the case that the different inputs that actually generated a different use case. So they would use labeling as a way of determining this uniqueness. Offline job servers did what they called classification. So the idea of classification was this idea of automated error diagnosis. So can I get the developer or can I get the operations person looking at this 5 steps ahead in a 10-step process of debugging? How much of this can I automate in the debugging process? The cab files what that would do is they would actually store the full dump if they wanted the information from an application. And so it's a completely separate process that they would then go about and actually give this to the developers if they wanted the full state of the application. Like I was talking about before, the automated error diagnosis system, labeling was trying to identify uniqueness, and it was a powerful way to scale data capture, which I'll talk about in a second. Server-side bucketing, so these offline job servers were doing classification. They called this system Bang Analyze, and it was to classify errors to maximize programmer efficiency. So they use this system for classification to be able to say, show me the last time I've seen some sort of memory corruption, within this part of the system. Show me the last time that I've been able to show this type of bug. And so be able to do these higher level statistics and intuition on the system. It was derived mainly empirically, so they did not come in with all of these algorithms to be able to do this, but what they did is they said, these are the kind of problems we've seen time and time again. Can we program in algorithms to be able to automatically classify them? The second goal of the system was progressive data collection. So stage one was they would generate this label and send it to the front-end servers. They would say, is this unique or not? Then if they haven't seen this error before, they would actually collect a mini dump, which was abbreviated stack with some of the memory as well. And then the third stage was the full memory dump into a cab file. So if they wanted more information from the developers would request it, they would get it. The really awesome part about progressive data collection is that they could do this on a massive scale, and they only needed one pair of SQL servers. So only 2 systems to be able to record every error on every Windows system worldwide, and this was in 2009. The third goal was statistics-based debugging, and so with such a large number of error reports, you can actually do data analysis across this data set. So they did this to do prioritization, finding hidden causes through correlation. So imagine the ability to say, is this crash in Windows actually most of the time from a third-party device? Or for a little bit more context, maybe let's say, is the input request, let's say it's an HTTP request that comes in, is it always of this type before to be able to see this error? And then the last part that was really cool is testing root cause hypothesis, which I'll talk about in a second. The really awesome part about this is that it was shifting debugging into a data analysis problem, which I talked about before. The last awesome part about statistics-based debugging is that they could release a solution and they could actually measure and see if it would if it would continue to happen or if there are any regressions. So the benefits to this system were, by and large, very, very influential at Microsoft, according to the paper. So it helped them do prioritization, helped them test hypotheses, and these other benefits. So what does prioritization look like? So according to their statistics, the naive way is let me sort my errors based on the volume of reports that I see. So let me knock out this error that I see the most, essentially. And this was an effective way for them to do prioritization. On the right here, you actually see a CDF of each of these different applications, and for the percentage of errors that actually fell into the top 20 error types. And so you see this very nice distribution of the top error type actually accounted for quite a bit of the number of errors. And so by being able to prioritize that way, you can actually knock out a number of errors immediately. The other thing that they pointed out in the paper was that there was an alternate way that they used to do prioritization. And this was centered around this idea of debugging locality. So if I'm actually trying to change this function, let's say I'm addressing a bug in this function, let me see all of the errors in this function, and let me actually prioritize based on that. And that way I can fix all of the errors within this function that are potentially within this function, I should say, and go from there. And so it provided a very powerful way to get more efficiency out of the team. With correlation, the mini dumps that they captured actually capture not just the state of the application, but also characterization information. So they called this the WMI, which included hardware info. So one such example is they saw a specific error where 96% of error reports came from a specific computers running a specific third-party device. It was important for them to realize that this bug was not happening on the scale of it was occurring the most. So it was comparing what they expected versus the deployment of this third-party device versus what is observed. So if I expect that 90% of computers are actually running this third-party device, that's big. But if only a small percentage of them are, but of this type of error, 96%, they could prioritize effectively. The last part that correlation kind of fits into is this idea of stack sampling. So tell me the function where I've seen the most errors, essentially, which is a really powerful thing to do when you can determine stability of a subsystem. The Bang Analyze system also allowed engineers to write hypotheses, test functions, on real live application state. So one example of this is that they had a plug-and-play lock in the Windows IUB subsystem. And what they did was we constructed an expression to extract the current holder of the lock from a memory dump, and then ran that across 10,000 memory dumps to see if their intuition was right. So maybe sometimes you guys have been out there in debugging and you said to yourself, if X is happening, then it must be Y. The problem with that is that it very much is intuition-based. And so having this kind of data store of all of this error data was powerful for them to actually test their hypotheses. So bringing all of this together, I actually wanted to share a war story from this paper that was really cool. Basically, in 2007, they had this really bad malware that they called Reno. And what this malware would do is it would actually cause your GUI to crash, and then when it would attempt to restart, before it would actually be able to fully restart, it would crash again. So you're kind of in this endless loop of crashing. Luckily for them, the Windows error reporting solution came up to a point the GUI came up to a point where they could actually report back the error. So they were seeing this repeated crashing happening on everyone that was infected by this malware. So the system itself was actually useless to the user. But when they started detecting this, they actually released a fix. And what they did was that every time now, when they released the fix, The problem with Windows is that you actually have to download a Windows update to actually get the fix. And so for people that were experiencing this error, they would actually show them a prompt to be able to download this fix automatically. So they would automatically identify the error that they were seeing and then actually propose a resolution path to the end user, which was really cool because it actually brings about this idea of automated error resolution as well. So not just diagnosis, but now the resolution path. And you can kind of begin to see the building blocks that they're building here with the Windows error reporting solution. So I called out this paper as well because they kind of took this to the next level in 2012 with performance debugging in large via mining millions of stack traces. So taking this postmortem debugging system and actually retrofitting it, sorry, not retrofitting it, but actually enhancing it to do performance analysis, which is a really, really cool idea if you think about it. So if they're capturing all these mini dumps that have stack traces in it, and then actually capturing them on the scale of millions, actually taking this data and actually making it a very large-scale profiler and trying to see where people are spending most of their time within certain functions, within certain execution paths. I recommend reading this paper. It's very math-heavy, but it's also a really cool paper talking about this. So this whole story about postmortem debugging doesn't really end on a very good note. I'm not going to try to convince you to use postmortem debugging all the time now. There are certain cases in which you want to use it, but I will say it's a very powerful method to handle a certain type of error and a certain class of errors. So if you have a memory leak or leaked resources, it can be a very powerful tool for you to capture this state and compare it to a future state, as an example. These data assets can actually be leveraged to gain further insights to your application. So like Microsoft did, it's not just about determining the root cause for a specific error, but you can actually gain insights into what your application does and how it operates. The problem is that postmortem debugging is incredibly painful, and it's hindered by a number of operational problems. And so if we think about this and have a conversation about ways we can open up the idea of postmortem debugging by building debugging infrastructure at our companies and in the places that we work. So not just using something like Elk, but also being able to leverage things like these core dumps and being able to upload them to centralized systems and being able to do centralized analysis as well can be incredibly powerful. And so the verdict is still out. Let's see if postmortem debugging can be a thing that that catches on. But that's it for the talk that I have today. I don't know if I'm supposed to ask for questions, or I'm just supposed to. You guys can leave if you need to. Sure. So for you DevOps guys or gals out there, it's interesting because databases, they're supposed to be very resilient to these kind of things. But if you look at, MySQL, if you look at Postgres, a common thing is actually seeing core dumps from them. But then they actually don't use and leverage this information the kind of way that Microsoft did. And so postmortem debugging can be a very powerful thing beyond root cause analysis. Cool, and I recommend, so I saw a lot of raised hands for Python, so I recommend looking at PyHeapDump. It's an incredibly powerful tool, pretty useful, and it could really help out, especially for the Python developers out there. Awesome, no questions. If you guys want to talk about this, I'll be around. I'm here at Surge. At Backtrace, we work on things like this, and we're actually working on a postmortem debugging platform. So trying to actually build something so that we can bring Windows error reporting to the masses.